In this video, we're going to look at something called a dipole moment. And let's take, for example, our HCl molecule. If we look at the hydrogen, we have a proton in the nucleus. And in a previous section, we talk about this electron orbiting the nucleus. And the electron can be contained anywhere in this particular sphere. And we're kind of going to make an approximation here, but what we're going to do is we're going to say that this electron right here is going to have a force of attraction with the nucleus. And that's essentially, there's this force of attraction here between the proton and the electron, and it can become fairly stable, this atom. But when we form a bond, what we're doing is we're taking another atom and we're going to overlap their orbitals. So this electron here residing on the hydrogen is not only going to be attracted to its own nucleus, or the protons in its own nucleus, it now can move around in this entire new sphere right here. So the probability of finding the electron does not solely reside over here on the left-hand side, the atomic radii for the hydrogen. It can be found also over on this side on the chlorine. So if we have an electron over here, it's going to be attracted to its own nucleus, and also there's going to be a force of attraction between the nucleus of the chlorine. And an electron residing on the chlorine is going to be attracted to its own nucleus and also to the nucleus of the hydrogen. There's also going to be an electron-electron repulsion between all the electrons over here in the chlorine and the hydrogen electron. So what happens is, if we look at electronegativity, okay, remember electronegativity is a measure of how much a particular atom wants an electron. So if we look at the values for this, hydrogen has an electronegativity value of 3.1, where chlorine has an electronegativity value of 3.0. So what this will tell us is the electrons will spend more time on the chlorine. So therefore, they are not equally shared. And this is going to lead to a partial negative charge on the chlorine and a partial positive charge on the hydrogen. And this is what leads to our polar covalent bond. And we can denote this by using a little delta symbol, where we have a delta positive and a delta negative. And remember, it's very, very, very hard to isolate one HCl molecule. So what we have is, if there's another HCl in close proximity, they're going to have the same partial positive and partial negative charge, and there's going to be a force of attraction, not quite as strong as an actual bond, but there is an attractive force between the chlorine of one HCl molecule and the hydrogen on an adjacent HCl molecule. And we'll look at these forces in a later chapter. But now let's think about what happens with NaCl. If we have a sodium chloride, the bond that forms here is a result of a transfer of electrons. So the sodium is going to have a full positive charge and the chlorine a full negative charge. So what happens is, if there's an adjacent NaCl, we can form another bond between these because we have a full negative and a full positive charge. And if there's another NaCl nearby, they're going to form this extended structure or an extended lattice in 3 dimensions. And this is what we can call a crystal structure, or for NaCl, we're going to call this the rock salt structure. So they will form these extended solids, and this will be a property of ionic compounds. So we're going to talk in later sections, in a few chapters back, the specific properties that are going to result from these dipole moments. But in this course, it is very, very important to recognize between something that's an ionic bond that forms an extended solid versus a polar covalent bond, which has these dipole moments, versus a nonpolar covalent bond, which is not going to have a dipole moment.